Welcome to the 6.1 video. We are looking at applications of trigonometry, and we're going to start with vectors in a plane. A lot of this will be familiar, or at least sound familiar from class. So our goal for this section is to look at vectors and vector operations. And then something new is that we're going to change a vector into a unit vector. So we're going to take a vector and say, what if I scale it back to the unit circle? We're going to look at direction angles, and then if we have time, we'll look at the applications of vectors. Why are they important? Vectors are used all the time when calculating things such as wind, especially wind on the path of an airplane. If we say headwind or tailwind, changing your bearing, things like that. So vectors are used all the time during travel and navigation. So to start with, I just wanted to remind you the difference between a point and a vector. A point is a location. So A comma B with rounded parentheses is the location. If I give a direction from the origin to that location, that would be its vector. And that's the vector in a standard position. So starting at the origin with its initial point on the origin. This is kind of a more formal definition than we created in class. A two-dimensional vector, two-dimensional because we're only looking at two variables here, A and B. So a two-dimensional vector is an ordered pair of real numbers denoted in component form. Component form is what we call those pointy brackets, A comma B. The numbers A and B are components of the vector. The standard representation of vector AB is the arrow from the origin to the point AB. We saw that on the last slide. The magnitude of V is the length of the arrow. It's the distance. And the direction of V is the direction in which the arrow is pointing. Oftentimes, we label that theta. The vector 0, 0 is called the zero vector. It has zero length and no direction. So imagine on a coordinate plane, it would just be really a point, but we need that point to be able to be a vector. And I'll describe why when we talk about adding and subtracting vectors. So the vector 0, 0 has no magnitude. You're not going anywhere. And since you're not going anywhere, you have no direction to go. Okay. So that's a more formal definition than we created in class, but the heart and soul of vectors is what we just described in class. For vectors, because it doesn't matter where in the coordinate plane it is, there are an infinite number of ways that we can draw each vector. Every vector, though, should have an initial or a starting point where it starts, a terminal point, which is where it ends. And we can draw equivalent vectors, meaning the same vector with a new initial point. So the vector that we have here is 3, 4. No matter where I start, if I go 3 units over and 4 units up, that will be the same vector, just in an equivalent location. It's in a new place, but the same directions. Okay. The way that we can calculate a vector from given points is called the head minus tail rule. Now, if you think about this, this is actually pretty intuitive. We would probably have used this even if we didn't have a rule for it. And you might recognize this as being very similar calculations to slope. Because really what we're doing is calculating the rise and the run, but we're not creating a ratio with it, right? With a slope, we look at rise over run. The vector is run, comma, rise, right? We're seeing how far do we go sideways and how far do we go up and down. And to calculate that, same expressions that we would use as rise and run within our slope calculation. For the magnitude, we derived this in class. We use the distance formula, which comes from the Pythagorean theorem, and we can use those same values. So if you have a vector, let's say I have vector v, and I have it in component form, a comma b, I don't need to use the whole distance formula. I can use just the Pythagorean theorem. Okay, so again, this is review. We talked about this in class already. So let's do an example. Find the magnitude of our vector represented by PQ, where P is 3, -4. It should have a little arrow on the side of Q, and Q is 5, -2. So the first thing I'm going to do is I'm going to graph the point 3, -4, and 5, 2. And I know that this graph is not pretty, but it's going to tell me I'm expecting a positive vector, right? I went to the right and I went up. Now, how far did I go to the right and up? Well, I went from P to Q. So I went from 3 to 5 is a distance of 2. I can do that as 5 minus 3 equals 2. Then I went from -4 up to 2. So 2 minus -4 equals 6. So I can say vector V equals the vector with directions 2, 6. And that's all there is to it to find the vector. Now we need to find the magnitude. So now we need to know what is the length of this arrow, which is calculating the hypotenuse of the triangle. So we can say R, we'll call it R for the radius, doesn't really matter, you could call it X, equals the square root of 2 squared plus 6 squared. So that's the square root of 4 plus 36, which is the square root of 40. 40 is 4 times 10. So we have 2 times the square root of 10. Square root of 4 is 2. I knew that 4 was a perfect square. That's kind of funny notation that is unique to me. Let me do it in probably the way that you've seen it. Okay, so the 2 comes out of the radical and the 10 stays in. So our magnitude is 2 root 10. We don't have units, so that's how we leave it. Okay, so what if I need to add vectors? Well, if I add vectors, that means I'm going a certain direction and then I'm doing that again, right? I can add vectors that are different by doing the same thing. So if I have 2 vectors and I wanted to add them, think about going along vector u and then going along vector v. I would just add their x's and add their y's. So if I start at vector v and then I add vector u, I just made a new vector u, there we go. Then the total distance, the distance that I add, will make this new vector. Okay, sometimes we call this the head to tail rule. Head to tail because I start my next vector at the head or the arrow of my previous vector. Okay, and that means that if I add the same vector to itself multiple times, such as 4 times, then I can just say v plus v plus v plus v, which just like with adding numbers, I can then write as 4 times v. So it's called a scalar because I'm adding a number of them. A scalar is just a number. 5 is a scalar, pi is a scalar. So if I say scalar multiplication, that means I'm multiplying a number times a vector. And in order to do that, all we have to do is multiply each component, the x and y components, by the same scalar. Let's look at an example. We have u and v. We want to find 3u plus v. So if I were to graph this, starting at the origin, u would be 2 and -1. There's 1u. And then 2u, 3u, and then v is to go over 5 and up 3. 1, 2, 3, 4, 5, 1, 2, 3. Okay, so that gives me an idea. I know that 3u plus v should take me over somewhere positive x value and 0 for the y value, it looks like. So let's try it. 3u is 3 times 2 comma -1. 3 times 2 is 6. 3 times -1 is -3. Notice that is what we got here. That's 3u. And then plus v is 5 comma 3. 6 plus 5 is 11. This is a V, and this is vector U. They're bolded, so that's why I'm kind of drawing over them so that we can tell that that's a vector. -3 and 3 is 0. So my final vector, 3U plus V is 11, 0. And that's what we expected from our sketch as well. I would say it's very helpful to sketch it so you have an idea of what your answer should be. That way, if you drop a negative or something, it is more clear why your answer doesn't make sense. Okay. Okay, so something new that we can do with vectors is calculate the unit vector. A unit vector is a vector with a magnitude or a length of 1. So as long as v is not the 0 vector, we can find a unit vector by taking a vector and dividing it by its magnitude. Or we can think about it as multiplying the vector by 1 over its magnitude. Okay, so whatever our vector is, whatever the length or the magnitude of our vector is, we can multiply it by its reciprocal to get a unit vector. That's all we're doing for a unit vector. Now, oftentimes those unit vectors are going to have radicals, it's going to have fractions because a vector's length often has a radical. So just keep in mind that you want to be careful, you want to be organized when you're finding unit vectors. Okay, so when we're finding a unit vector, we multiply everything by 1 over its magnitude. That means we can write our vector. Remember, we used magnitude, we used r in class, times cosine of theta, r times sine of theta. So then the unit vector is going to be just cosine and sine, just like the point on the unit circle. So now we're going to apply this. Let's find the unit vector. So if I look at this vector, 2, -3, that vector has a length of more than 1, right? 2, -3. So in order to make this a unit vector, I want to take the vector, divide it by its magnitude. So we need to find its magnitude. 2 and 3. To find the magnitude, we need to do 2 squared plus 3 squared under the square root. Remember, that's the distance formula. So that's 4 and 9 gives us the square root of 13. So I'm going to have 1 divided by the square root of 13 times 2 comma -3. So now we're going to apply what we learned for scalar multiplication. That gives us 2 divided by the square root of 13 comma -3 divided by the square root of 13. If we're being formal, we should rationalize, and you should always be formal. So that's 2 square root of 13 over 13, comma -3 square root of 13 over 13. That is the unit vector. So the unit vector, we often write it with a U, but not all vectors that are called U are unit vectors. So just be careful and make sure if you're going to assume that it's a unit vector, make sure it says that it's a unit vector. And what's special about that is that the magnitude of U equals 1. That's what makes it a unit vector. Okay. We have some standard unit vectors, these vectors that have a length or a magnitude of 1, and that is our component vectors where we have just 1, 0 and 0, 1. So if we were graphing with these, I would be kind of like X, but not the point, right? Not a coordinate, but actually a direction to just go 1 unit to the right. And so we could have -I be 1 unit to the left. Then we have 1 unit up is J, and 1 unit down is -J. Okay, and we can always write vectors in terms of I and J by just saying we have whatever our A value is times I, which is a vector, and then whatever our B value is times J, which remember J is a vector. So this is still a vector. Okay, so let's do an example here. We want to find the components of a vector with a direction angle of 120 degrees and a magnitude of 8. So components means we want to find the vector in the pointy bracket form. but we're not given distances now, we're given a magnitude and a direction. So if we're looking at that vector, remember magnitude and direction, we can use sine and cosine. So we're going to say vector v equals magnitude times cosine of theta, comma, magnitude times sine of theta. So we're applying this formula. So that's 8 times cosine of 120 degrees, comma, 8 times sine of 120 degrees. I'm going to relate this to the unit circle. So 120 degrees is here. That gives me negative 1/2, comma, root 3 over 2. So this is 8 times negative 1/2, comma, 8 times root 3 over 2 gives us negative 8/2, comma, 8 root 3 over 2. Simplifying that, we get negative 4, comma, 4 root 3. So this is the component form of the vector that we were given with the magnitude and direction, applying that formula that we talked about in class.